All right, so on the screen in front of you, I have a triangle that is special in a certain way, although it's not one of the two special triangles that we talked about at the beginning of this lesson. In fact, this is something that we call an equilateral triangle. We call it equilateral because it has all equal sides. Now again, in geometry, because our images are subject to the error of the drawer, that would be me, you may not be able to just look at it and take a tape measure and measure out this triangle and find that, oh, all sides are equal, because I might have messed them up a little bit. However, you can see these little hash marks here. And in geometry, whether you've taken it or not, I can explain this very simply. Anytime you see one hash mark on multiple lines, it means that those lines are all equal to each other. So even though I might have a little bit of an error in my own drawing, I can communicate to you, as my other fellow mathematicians, that these three sides are the same. Now, something we know about triangles, again, some of you have taken geometry and will remember this, and some you may not know this, but if we have an equilateral triangle, which means equal sides, we also have an equiangular triangle, which means we have equal angles. So if a triangle has equal sides, it also means that the angles have to all be equal as well. And since in geometry we figure out that every triangle has 180 degrees in it, so if all of these angles are going to be the same, that means this is 60 degrees, this is 60 degrees, and this is 60 degrees. So this is an equilateral triangle, meaning equal sides, or we can also call it equiangular. It has equal angles. Now, here's the part where we're going to discover our special triangle. Remember, we had 45, 45, 90, which we discussed in the previous video, and we also had 30, 60, 90 triangles. And if I take my equilateral or equiangular triangle and I try to draw a straight line here down the middle and divide it in half, you'll notice if I divide it right down the center, I can do it in a way that this is a right angle. So we can tell that it's a right triangle. I know that this angle over here is 60 degrees because I haven't changed it. And I also know that I've split this angle here perfectly in half. Now I could prove that if we were in geometry class. I think it's clear enough in this picture that you probably will believe me. If for some reason you don't, I can always spend some time proving that later. But just like we've cut the opposite side in half, we've also cut this angle in half. And so this, instead of being 60 degrees for the full angle, is 30 degrees. And if you look at this triangle that we've created, we have a 30, 60, 90 triangle. So if you take a 60, 60, 60 triangle, or an equiangular, and cut it in half, we get 30, 60, 90. Now why does that matter to us? Well, primarily it helps because we're trying to figure out the side lengths, or the missing side lengths. Let's do a different color. Let's do, oh, that's kind of an ugly color. We'll do more peach. We're trying to find the missing sides of a 30, 60, 90 triangle with a hypotenuse of 1. So let's look at what we have here. We have a 30, 60, 90 triangle. The hypotenuse is this one here, right? Down the side, across from the right angle, and we know it's 1. So the question is, what is this side and what is this side? Well, one of these two sides is going to be pretty easy. And I'll give you a hint. It's not the one in red. It's this one over here. This one is, we already said, half of the full side. And we knew that this originally was an equilateral triangle. All the sides were the same. So this side here used to be 1. If I cut it in half, it's 1/2 because it's half of 1. So that wasn't too crazy and difficult to do. So this is actually not a mystery side. We already know that this side of the triangle right here is 1/2. So that means we only have one missing side of our 30, 60, 90 triangle, and it's this one, this longer leg. We have the hypotenuse is 1, the short leg is 1/2, so the question is, what is this longer leg's length? And just like in the 45, 45, 90 triangle example, we were able to figure out the missing values using a squared plus b squared equals c squared. Remember, I told you in class we use this over and over and over again, and I wasn't kidding. We use the Pythagorean theorem everywhere. And here's another example. So let's say a squared is the short leg, so that would be 1/2 squared. Plus b squared, we'll make b the missing side. We'll call it just x, because we don't know what it is. We'll call this x. There. Actually, it kind of looks like when I crossed this out down here that I meant x. That's not x. That was me crossing it out. So 1/2 squared plus x squared equals the hypotenuse squared. And we said the hypotenuse is right here, and we know it's 1. 1 squared is just 1. So 1/2 squared plus x squared equals just 1. Let's try to simplify this. 1/2 squared is 1/2 times 1/2, which gives us 1/4. If I want to isolate the variable, that means I have to subtract 1/4 from each side. That's going to leave me with x squared equals 3/4. Because this is 1 is 4/4. I subtract 1/4 and I get 3/4. And then I need to take the square root. Again, when we undo a square using a square root, we're supposed to say plus or minus. But we're talking about measurements of a triangle, so we don't really want to get a negative answer. So it's okay for me to ignore the plus or minus here, and we'll just say x equals the positive square root of 3/4. The square root of 3/4 is the same as the square root of 3 over the square root of 4. Let me kind of do that over here. So remember, if I have the square root of a fraction, I can also say that's the square root of the top, or the numerator, over the square root of the denominator. Why do I care about that? Well, remember, we don't like roots in the denominator. And we're not going to have to do a lot of work here because the square root of 4 is a whole number. Square root of 4 is just 2. So we don't have the problem we had last time. No roots in the denominator. And so this stays the same, the square root of 3 over 2. So the value of x, in this case, the missing side, is the square root of 3 over 2. So that means right here, this side is the square root of 3 over 2. Let's take this picture. Make sure you kind of have it written. I'm going to erase it and make a nice clean copy so that you can have one that looks like our original picture in the original topic video, topic 1. So I'm going to get rid of that. And remember, your first 30, 60, 90 triangle looked more like this, with the right angle here. This is the smaller angle, so we know it's 30. This is the larger angle, so we know it's 60. Let's see if we can fill in the blanks now from our little proof that we just did. Remember, we're saying the hypotenuse is 1. That's just an assumption we made at the beginning. We said that the shorter leg, really you can imagine that this is actually half of an equilateral triangle, which means that this side right here is half of 1. So this is 1/2. Let me get rid of those extra marks. This is just 1/2. And then using the Pythagorean theorem, we showed that the longer leg would have to be root 3 over 2. So for any 30, 60, 90 triangle, which is one of 2 special triangles, with a hypotenuse of 1, the side lengths are 1/2, root 3 over 2, and 1. All right, I know I have not showed you how this applies to the unit circle yet, but that's okay because we're going to spend some time in class talking about that. But I want to make sure that you start out having a master copy kind of what a 45, 45, 90 and a 30, 60, 90 triangle should look like, specifically when the hypotenuse is 1. So make sure that's in your notes. That's all for tonight, and I will see you tomorrow in class.